We've talked about the Hubble tension a few times here on the channel, and this is, of course, the crisis in cosmology. This idea that if you measure the expansion rate of the universe in relatively nearby parts of the universe, you get one number, and when you measure it in the cosmic microwave background radiation, which is like the earliest point you can measure it, you get a different number. And those two numbers do not overlap. Their error bars are not in the same range. And so either someone made a mistake with a measurement, or there's some new physics that need to be figured out to help explain what's going on. And one of the proposals is called early dark energy. And this is different from the dark energy that is accelerating the expansion of the universe today, but another form of dark energy that appeared early on in the universe and gave it a very quick kick in expansion, but then subsided. And this has made some testable predictions about the universe. So my guest today is Dr. Sunny Vagnozzi. He is an assistant professor at the University of Trento. He wrote a recent paper where he made a bunch of predictions about what we should see in the universe if this early dark energy is the answer for the Hubble tension. And we talk about that, and then just like a whole bunch of other concepts in cosmology and such. Now, I just want to warn you in advance, this is a very advanced conversation, mostly to me. And so I am stopping Sunny and asking him to clarify. I'm attempting to put what he says in my own words to make sure that I understand before we proceed. And so if you don't want to hear that, this might not be the interview for you. But if you want to understand this early time in the universe and the way astronomers make these kinds of predictions, I think you'll get a lot out of this interview and sort of close a lot of gaps in knowledge about cosmology, the Big Bang, dark matter, dark energy, all of those kinds of concepts. All right, here's the interview with Dr. Sunny Vagnozzi. Sunny, what's your description of the Hubble tension?
Okay, so my description of the Hubble tension is a discrepancy between different ways of measuring probably the most fundamental number in the universe, the only scale in the universe, if measured at different extremes. Let's put it this way. If I measure my height from head to toes and from toes to head, I would expect to get the same answer.
Yeah.
And in the case of the universe, we're not. With the difference that one of the two measurements, let's say from head to toes, does assume a certain model, let's say for how I grew during my childhood and so on. So either there's something wrong in this measurement, or my assumption of how I was as a teenager is wrong. Let's put it in this very simple terms, if it makes sense.
Yeah, no, that's great. I've never heard that method description before, and I really like that because it feels so intuitive. Like, of course, you're going to get the same answer, and yet if you get a different answer when you take the measuring tape and go from your feet to your head or your head to your feet, and you get a different number, like that would be really weird. So obviously there have been a ton of responses to the Hubble tension. Maybe either of the measurement methods isn't correct, and that's fine, but then more exotic ideas have been proposed. So what are some of the like not measurement error ideas that have been proposed to try and answer this?
Sure, there's probably like between a few hundred and 1,000. So I'll just mention a few of the least
we don't have
crazy
time for
ones.
that.
Yeah. So early on, before some aspects were well understood, people were looking at modifications of the universe at what I call late times, so after recombination, after the CMB formed. Examples of these crazy models could be something called phantom dark energy, for example. So phantom dark energy is a form of dark energy which not only makes the universe accelerate, but it makes it sort of, let's say, super accelerate. It accelerates so fast that you might get to a point which is called Big Rip, where the space-time under us is expanding so fast that it rips apart everything like atoms, single particles, and so on. So phantom dark energy was one possibility. Or in general, any crazy dark energy component which goes even faster than the usual dark energy. There was one example. And this class of models is not a serious contender anymore because it's ruled out by measurements of what we call baryon acoustic oscillations in galaxy survey, basically the imprint of frozen sound waves from the early universe. Another class of less crazy models is, say there was some extra radiation which you can parameterize as a number of neutrinos greater than 3. That could also help in raising the Hubble constant. But this is a class of model instead which operates before a combination, before the CMB forms. So now you already start to see this dichotomy between early universe and late universe models. Another model which is still very popular nowadays is called early dark energy, and it works as follows. So say there was some component just before a combination which looked like dark energy, and it speeds up the expansion of the universe. Well, it doesn't really speed it up, it just makes the universe, the expansion decrease less slowly. That could have an effect which overall acts to reduce the sound horizon, so the distance traveled by sound waves in the early universe. And because of how things work in cosmology, reducing the sound horizon has to be compensated by increasing the Hubble constant. So that's a model which is still very much, being explored nowadays. It hasn't yet been killed. There have been claims of it being killed. I think none of them are totally convincing yet. But if early dark energy is the answer, we do expect to see it very convincingly in the next 5 years. So let's put it this way. In the next 5 years, in 5 years from now, either we'll know early dark energy is very close to being the answer, or we won't be talking about it anymore, in my opinion. It's either white or black.
Right. And the whole reason that I reached out to you was you wrote a paper going through the kinds of the kind of evidence that we could look for in the universe to confirm whether this early dark energy did play a role in the expansion of the universe. So let's go through these in whatever order you want. Well, like if the universe did go through this, I don't know, less of a slowdown on the expansion of the universe. I guess the first part is like, what time period did that happen in? Like when would have early dark energy kicked in, and when would it have ended?
Sure. First of all, let me just clarify one thing. So my paper, it wasn't just about early dark energy. It was about anything crazy, anything beyond standard at early times. Early dark energy is an example, but it's not the only one. Okay,
this is great. Good.
Yeah. That being said, early dark energy will have to kick in around, 200 to between 100 and 300,000 years after the Big Bang, and it has to die very quickly after it kicks in. So that's sort of a problem, because you have to explain why this component suddenly appeared and why it suddenly died. So there's a bit of a coincidence problem, if you get what I mean. But that being said, even if we ignore that, the point of my paper was that I believe whatever crazy thing you do before recombination in the early universe, that's never going to be enough. So my observation was based on, it's mostly based on hunches and empirical observations. So what I noticed was, a lot of very smart people have tried to modify the early universe in all sorts of ways over the past, 7-8 years. And the best they have gotten to is to push the inferred value of the Hubble constant up to, 70 or 71 in a best case, which is very far from, 74, which you want. And this has got me thinking, maybe the real problem is that something new at early times alone is never going to be the full answer. And in my paper, I try to make my case for this argument. So I introduced this 7 hints, which are very varied in nature. These are the ones I guess you want me going through.
Yeah, definitely.
Sure, okay.
I mean, because I think like when we talk about dark energy and when we talk about dark matter, I think that the complaint that we get from people is, well, astronomers are just making this up. Like, why do they have to invent things? And yet,
epicycles,
Yeah. And yet the observations are numerous. They are independent lines of evidence that something very strange is going on. And every attempt to remove the error, the uncertainty, has just made the problem weirder. And it just makes it more like that there is something going on here. And so I think what's really satisfying in this kind of situation, if we can't figure out what it is, then at least trying to figure out what it isn't. Trying to disprove hypotheses is a very satisfying way to go about this search. And so I think what we're going to do here is provide a mechanism that people can disprove hypotheses.
Yeah. So, I'll take my 7 hints not in alphabetical order, but somewhat in, let's say, scientific order. Okay. So 2 of these hints are related to the high level of consistency of Lambda-CDM. Okay. So our standard model, it has only 6 parameters, but it has an extremely high level of internal consistency when you fit it to the data, which is very hard to match the moment you tweak it and you introduce something new. So I focused on 2 examples of this consistency. The first one is about the appearance of different scales in cosmology. So when we look at cosmological observations, in particular how galaxies cluster, and we study them statistically, what we get, we can basically extract 2 different scales out of it. One is the scale of the sound horizon. So we see an imprint of how far sound waves traveled between the Big Bang and when they were frozen at recombination. That's the first scale. And the second scale we see is about how big the universe was when the amount of matter and radiation was the same. So this is called the equality scale. Now, from both of these scales, you can, in some way, infer the Hubble constant. And in Lambda-CDM, when you do this, you get 2 values which are in very good agreement. Okay. Now, the moment you introduce something new beyond Lambda-CDM at early times, there is all the reason to believe this agreement is going to go out of the window for the following reason. Early dark energy, for example, requires something very new around matter radiation equality, but not at recombination. So you would expect one of these 2 scales, which is sensitive to equality, to be very much impacted by early dark energy, but not the other one. So the question is, why do both scales give you the same value of H0 in current data? This is a consistency which is very non-trivial and very hard to maintain the moment you put in new stuff between matter radiation equality and recombination, which is in that period I mentioned to you between 100,000 and 300,000 years after the Big Bang. So that was one of the hints. It's of course this is not a mathematical proof. I'm just stating, whatever you do there, it's not going to be easy to maintain this consistency.
And so, sorry, just to go back for a second there. So that idea of the acoustic oscillations early on in the universe, like we always say that, in space, nobody can hear you scream. And that's because there is no medium for the sound to transmit.
Yeah.
But early on in the universe, particles were close enough that sound did transmit through the entire universe.
Oh yeah.
And
Absolutely.
I wonder what it would have sounded like.
I haven't actually thought about what's the frequency of this oscillation.
Yeah.
I don't think it would be, hearable by humans, but one can easily work that out, in fact.
Yeah. And so just as we get, say, sound waves, when you think about like sound waves moving on a speaker and then you get little particles bunching up together on that speaker, you got sound waves moving through the universe and you got matter piling up into regions that matched the peaks and troughs of the sound waves, and that freeze out. That's that moment that now the sound can no longer transmit from particle to particle, and so whatever you're left, wherever the concentrations are, wherever the gaps are, that then proceeds into every part of the universe, from the early galaxies to the large scale structure. Like the large scale structure of the universe that we see today are those peaks and troughs that we saw in the cosmic microwave background billions of years ago.
That's pretty much correct. Yeah, you have these peaks and troughs, these regions of high density, which then become even higher density because gravity, exacerbates any overdensity. Okay, so any small deviation from the background density is going to grow exponentially under the effect of gravity. So that's how you and I are here today. Eventually, yeah, that's pretty much it.
And it is amazing to me how many aspects of the universe have been worked out just by these baryonic acoustic oscillations. Most recently, astronomers detected or indirectly detected the presence of cosmic of neutrinos from the Big Bang just in the shape and size of the large-scale structure of the universe, that you couldn't get what we have without there being neutrinos early on in the universe.
Yep. Yeah. There was a very non-trivial measurement of this so-called phase shift, if that's what you're getting to.
Yeah.
It's very non-trivial if you think about it. Yeah.
So then, sort of back to what you were talking about, and I'm going to apologize to the listeners because people are like, "Oh, don't interrupt the guest." But this is very complicated stuff, and I feel like if I don't understand it, then it's going to be, maybe the audience totally understands it, and I'm just like a dummy. But I just want to make sure that I've got these fundamentals right. So in other words, that there are these two measurements, they agree nicely, they help provide sort of independent lines of evidence that support the measurements of Lambda-CDM and provide evidence for what that early measurement of the universe is. And you've got, if there is this early dark energy, then those numbers should not be the same in the way that they are. They would be powerful evidence for early dark matter, but we don't see that. We see them agree with each other.
Correct. Yeah. With the caveat that the error bars are still large enough that there might be something lurking within the error bars. Okay. But this consistency at the current level is already pretty puzzling if there was something new beyond Lambda-CDM at early times. Yeah, that's pretty much one of the 7 hints. And another of the hints is about a similar level of consistency. It's a bit more technical here. It's due to something called the early ISW effect. So let me try and put this together. So in the early universe, you do not have a perfectly smooth background, but you have, peaks and troughs, as you put it, and CMB photons are traveling in these peaks and troughs, and in particular they travel within peaks and troughs which are varying in time. They are slightly decaying because at the time the CMB formed, there is a bit of radiation which makes potentials decay. On the other hand, if there was only matter, these potentials would be constant in time. Now, you can try and what you can do is try to work out the strength of this effect and parameterize it in terms of some deviation from the Lambda-CDM expectation. And when I did this exercise, I found the strength of this early ISW effect to be completely in line with what you expect from Lambda-CDM within, 0.3 sigma. So it's a perfect agreement. Now, if you threw in dark energy at early times, what it's going to do is it's going to have an effect similar to that of radiation. So it's going to help these potentials decay. So a CMB photon starts entering a potential well, but by the time it gets out, the well is shallower. And this is something you are going to see in the CMB. You can quantify this with the amplitude of this early ISW effect. And I showed that if early dark energy is the solution to the problem, you would expect a 20% enhancement in this early ISW effect, which we do not see. And again, this is a indication of how consistent Lambda-CDM is with not just the data as a whole, but different bits and pieces of the data which you can extract in some way. And that's very hard to maintain the moment you go beyond. And this is true not only for early dark energy, but anything you threw in at early times, which makes the sound horizon decrease. So that's another of the 7 hints.
And I think I've got that one. I think I understand. So let's continue.
Okay. So another series of hints instead are about not so much the early universe itself, but the late universe. So what I show in this other series of hints is the fact that Lambda-CDM does not seem to be the end of the story at low redshift. So say between redshift 0 and 10 in the last couple of billion of years, let's put it this way. Actually more than that, in the last, I want to say 12 billion years. There is something missing in my opinion. Okay, and the first of these hints is about the ages of the oldest astrophysical objects. So I guess you're old enough to remember the fact that between the 60s and the 90s, there were reports of objects like galaxies being older than the universe itself. Mm-hmm. And that's because people did not know about dark energy. But if you put in dark energy, you make the universe old enough to accommodate all these objects. Okay, now it turns out that the age of the universe at any redshift is inversely proportional to the Hubble constant. So if you can find the oldest objects in the universe at all redshift, you can use this to put an upper limit on the Hubble constant, simply because if the Hubble constant was larger, the universe would be too young to accommodate these objects. So I did this exercise. I went and looked for the oldest galaxies, the oldest quasars up to redshift 8. So what I basically made a census of the old guys in the universe. I found like 114 of them. And when I do this exercise and try to get an upper limit for the Hubble constant, assuming Lambda-CDM, what I get is an upper limit of about 72.5 to 73 at 2 sigma at 95% confidence, which is, it's in tension with the local measurements by Adam Rees and his group. So if we take this seriously, what I'm telling you is the universe with the Hubble constant measured by Adam Rees, and if we assume Lambda-CDM, is slightly too young to accommodate its oldest objects. Okay, the obvious way to fix this would be to introduce a bit of new physics at late times, which makes the universe old enough that you can fit these objects. Okay, and something like this phantom dark energy I mentioned earlier would go indeed in the right direction. And you don't need too much of it, you just need a bit. But it turns out this bit would also go in the right direction to help raising the Hubble constant, okay, beyond what you can get with early universe physics. And so that's another of these 7 hints.
And so with, you mentioned Adam Rees, he leads the team that does just the most exquisite measurements to Cepheid variables, and is the Nobel Prize winner, I think.
2011.
And is responsible for the, I don't know whether it's the head to foot or the foot to head measurement of the universe, but the one that calculates the expansion rate of the universe from objects that are relatively close to us in time.
That's right.
And so you were able to, and at a certain point, you switch over to the other method when you're looking at the cosmic microwave background. But ideally, the farther and farther we look back in time, closer and closer to the beginning of the universe, we are getting, hopefully we get the same number. And at a certain point, there'll be a flip. You're like, right there, that's where something changed. Or maybe there won't. And so were you using James Webb data to measure these galaxies? Because there's been a lot of new measurements coming out at galaxies that are in those regions,
Absolutely.
Within the first 1.5 billion years after the Big Bang.
Yeah, I haven't yet, but it's something in the back of my mind indeed. The only reason I haven't yet is that there's been a bit of controversy about whether we can trust the redshifts of James Webb galaxies. And it makes a huge difference if you have a galaxy, say, being 1 billion years old at redshift, 8 or 3. Okay, it makes all the difference in this type of argument. So I am indeed thinking about this, but I'll wait until I can fully trust those redshifts. That's the deal.
And that's interesting because, we've had a lot of, like, when Webb first came online and we saw all of those papers coming out, we were seeing, galaxy discovered at redshift 17. I saw 22, that we're seeing galaxies that are maybe 250 million years, 215 million years after the Big Bang. Yeah. And then, of course, that led to a lot of people kind of saying like, oh, James Webb overturned the Big Bang. But now much better analysis is getting done. Those distances are scaling back and we're getting a much better accumulation of those distances. Do you think, like, and so what would it take for you to go, okay, I'm ready to make these distant calculations now based on what I think is good data?
Sure, spectroscopic confirmation. So if I had redshifts which were confirmed via spectra from independent telescopes, then I would fully trust them. Now, that being said, I have thought about JWST in the context of the Hubble tension. I had a paper recently, actually, where we looked at some of these crazy models at late times, but it turns out the type of physics which would make structure form fast enough to see galaxies by the time Webb sees them, if you believe the redshift, goes in the same direction of the type of physics you need to make the universe older or raise the Hubble constant in the late universe. So it all points in the same direction if we take Webb seriously.
Yeah, and so the age of the galaxies in the universe fits within the universe nicely if there is this additional rapid expansion early on. Like it improves what you're saying is that it actually leans more towards early dark energy, if that's what you find.
Not necessarily. It leans towards actually something new at late times after recombination. Early dark energy may potentially make the problem worse, I would say, in the sense that early dark energy models tend to require a larger value for the matter density because of the effect I told you before, the early ISW effect. They need to compensate it with more dark matter. And this more dark matter, I want to say, makes the universe younger at all redshifts. So it does sort of go in the wrong direction for this type of problems.
But I guess then if there is some kind of short-term rapid expansion early on in the universe, not at that 200,000 years, but maybe something after recombination, that would work.
If it goes in a certain direction, if you have something like phantom dark energy, it turns out it makes structure form faster, which is the type of thing you want.
Right.
So it really depends. In technical terms, it depends on the sign of 1 plus the equation of state. If that's negative, structure forms more easily. If it's positive, you're actually doing the opposite effect. You make structure even more difficult to form. So the sign of the equation of state of dark energy is crucial for this endeavor.
Excellent. Okay, move on.
Okay, so another hint is actually very similar to the previous one. So the previous one is about the absolute ages of old galaxies, but it turns out you can also use the relative ages of old galaxies to measure the Hubble constant, and that's an idea called cosmic chronometers. And if you take cosmic chronometer data seriously and try to fit it using Lambda-CDM, you get a value of H0 which is spot on the Planck value, like 67 plus or minus 3, which, if you take it seriously, tells you, okay, Lambda-CDM cannot be the end of the story at late times, because when you analyze this data, you can analyze it making no assumptions about what happened at early times. Simply the data doesn't care about it. So whether or not you had early dark energy, something crazy at early times, this is telling you, no, there has to be something beyond Lambda-CDM at late times anyway. And this something would also go in the right direction of helping with the Hubble tension. So the nice thing about relative and absolute galaxy ages is the fact that when you work out the age of the universe at the redshift between 0 and 10, you have to solve a certain integral. But this integral doesn't care about what happened before recombination. Simply, it's a completely subdominant contribution. So whatever conclusion you draw, it's independent of what was in the early universe. Lambda-CDM, early dark energy, whatever you want, it doesn't matter. The conclusion you draw is you need something else at late times, which is where the data cares about.
And it's interesting that you get a measurement of the age of the universe from this method, the relative ages of the galaxies, that is more in line with the Planck measurement of from the cosmic microwave background. Like it seems like that's like it's all alone against everyone else that's coming up with measurements that are similar to the Cepheid variable method, and yet actually there is this at least one. Are there others that match?
A caveat. I would say there's an important caveat here, because all the other measurements you mentioned which agree with the Cepheids are all in the local universe, but these relative ages of galaxies are in the high redshift universe between 0 and 2, so they are not local in the sense if you were to bet your house on them, you should bet on them matching Planck and not Reese, because they are in the realm of non-local in the sense. They are not close to us, not by any standard in this sense. Does it make more sense now?
Mm-hmm. Yep. But still, I guess just like it is still like, again, if both measurements are right, and then the measurements that are coming from the farthest parts of the universe are starting to all agree with each other in the same way that the measurements from the close parts of the universe are all starting to agree with each other, and yet their error bars don't overlap.
Yeah, that's true.
So like this doesn't help. Like this makes the problem more puzzling and makes and makes the search for alternative physics more compelling.
I agree. And I think mathematically speaking, the problem is you have an over-constrained system. You have very few physical variables you can constrain and more data than your variables. So you have like a system with more equations than unknowns. And if you fit this system of equations with Lambda-CDM, except for the measurement by Adam Rees, everything agrees. But when you start fiddling in with new physics, you might even help with H0, but then you usually screw up with 2 or 3 of the other equations. Let's put it in this way, in mathematical terms. So again, we go back to the fact that it's very hard to maintain the level of consistency you see, internal consistency you find within Lambda-CDM. Of course, this makes the search for new physics more compelling, as you said.
Yeah. By my count, I think we have one left. Is that right? One more hint?
Yeah, a couple more, actually.
Okay.
Well, one more is very similar to this hint I just mentioned. It's really about, if I try and infer the Hubble constant in a smart way which doesn't care about early universe data, then what do I get? And again, you get something which is spot on with Planck. But this is really technical, so I think it doesn't make sense to cover it here.
Okay, no problem.
Yeah. I want to go through another more controversial hint, which I called in my paper descending trends. So, okay, let's put it in this way. If we look at the Hubble constant in this way, we have a high measurement from Adam Rees in the local universe and a low measurement at redshift 1100. But it turns out, mathematically speaking, if the Hubble tension is due to new physics in the late universe after recombination, you should see an evolution of the value you infer at each redshift, going between the high value at redshift 0 and the low value at redshift 1100. Okay? And if you do see this evolution, that's an incontrovertible mathematical sign that something is wrong in between these two measurements, so between redshift 0 and 1100. So the question is, have we actually seen signs of this? I call them descending trends. And the answer is yes. The first one was reported by Holy Cow, the strong lensing measurements of H0. You take some quasar image which is strongly lensed and you use it to infer the distance to the quasar and therefore H0. And in 2019, they had 6 quasars to make these measurements. And they reported a measurement from all 6 quasars combined. But then they did the following game. Let's say we look at each quasar separately and each is at a different redshift. And let's plot the value of H0 from each quasar as a function of its redshift. And they see precisely this very curious descending trend at a significance of about 2 sigma. So there was a first interesting hint in this sense. And between 2019 and now, people have looked at different combinations of late-time data beyond holy cow, like combining, BAO, supernovae, these cosmic chronometers, many different combinations. And many of them find the same trend here, which, again, if you take it seriously, it tells you, no, there has to be something beyond Lambda-CDM at late times after recombination with a significance of about 2 sigma. And again, it would go in the same direction of helping with H0 in pushing beyond what early universe models can achieve. So that's pretty much this other trend. This other hint.
Now, you said early on at the beginning of this interview that we should be able to start getting some answers within about 5 years. Why did you make that prediction of time?
Sure. Okay. Because if there is something funny in the early universe before recombination, it is going to show up in the CMB at the level which is still hard to detect with Planck data. It will show up both in the temperature and polarization pattern of the CMB. Now, in the next 5 years, we are going to see some brand new data from brand new CMB experiments. The one I'm mostly thinking about is called Simon's Observatory. So it's a ground-based telescope based in the Atacama Desert. And it's going to see first light, I think, in 2024 or 2025 at worst. And in the next 5 years, I would expect we have the first batch of data. And going back to what I said, if early dark energy is the solution to the Hubble tension, we should see it in Simon's Observatory data at something like 15 sigma. That's why I said either we'll know early dark energy is the end of is the solution, or something very close to a solution, or we won't be talking about it in 5 years. That's why I made this very bold prediction. But
right.
I think it's reasonable.
That the Simon's Observatory will be able to make that measurement with enough clarity to decide it either way. And
That's
either
right. That's
rule
right.
it out or keep it in. That's really
right.
interesting.
And beyond SO is Simon's Observatory, and CMB S4 is another planned ground-based experiment, which will be even more precise than SO. I don't know what the status there is, but if early dark energy is the solution, we'll see it at many sigmas confidence level in CMB S4.
Right. And neither of those will improve upon the Planck measurement of the Hubble constant in the CMB. Like, that number is as precise as astronomers could want, pretty much.
Yeah, almost. Yeah, pretty much. I mean, there's not terribly much you can do to improve in that sense, because H0 is mostly measured through geometrical background effects in the CMB. But here we're really talking about effects at the perturbation level, which don't really help much in nailing down the Hubble constant beyond what we already know now. At the level of CMB, of course.
So I guess, what would be a method for more precisely measuring the Hubble constant at earlier points in the universe, say within the first few billion years, to try to catch that switchover that maybe isn't available yet? I mean, is it in gravitational waves, some kind of combination of gravitational waves and electromagnetic waves? I mean, what if thinking about all of the proposed ways of measuring distance in the early universe, what's the one that you think could be the most productive?
Yeah, just to be clear, we can only really hope to measure distances after recombination. I think one method which is interesting.
And so just like when was recombination? Like, what time in the universe?
380,000 years after the Big Bang.
Okay, so that's the CMB that we're seeing.
Yeah, exactly. So between the CMB and current redshifts we can probe, I would say the next big player in the game is going to be neutral hydrogen, or in general what we call line intensity mapping. So you go after a certain emission line, and that allows you to see at redshift, potentially up to, I think, 30 or more, I want to say. So there, you could, if you really measure the expansion history there, it could be, I don't know if you would see this switch on you mentioned, but it would definitely help either consolidate or refute Lambda-CDM in a range which we currently simply cannot test. We don't have the capabilities.
Right. And so what you're talking about, this is this sort of behavior of neutral hydrogen to throw out photons at a very specific wavelength occasionally. And that can be measured with a certain kind of radio telescope. And, the largest that's in construction right now is the Square Kilometer Array.
That's right.
But there are other sort of, they've been proposed, like, we've talked quite a bit about building a radio telescope on the far side of the moon.
Oh, yeah.
This is the kind of measurement that they're going to try to detect these giant clouds of neutral hydrogen at, within tens of millions of years after the Big Bang.
That's right. That's precisely what they're going to do. Yeah.
And so you're making that redshift measurement in the same way that you would be making a redshift measurement of a quasar that is a few billion years after the Big Bang, or one that is we're seeing just a few 100 million years away from us, light years away from us. So it's that same technique. And so that would get you almost to the recombination, almost to the CMB.
Not quite, but in terms of years, yes. In terms of redshift, no, because of course it's not a linear mapping between the two. It's the relation between years, time, and redshift is very highly nonlinear, and it turns out that what really matters, I would say, is redshift. So you would get up to redshift maybe 30, but I know of no way to close the gap between, redshift 100 and 1100.
Right.
I simply don't know how you do that.
Because there just wasn't anything there
there is some neutral hydrogen, but not. Yeah, exactly. I have no idea how you would illuminate that. And I think the signal will also be too weak, because you also have to consider it's being redshifted as it comes to us. And that makes it even more challenging to detect any signal. I'm sure someone will figure it out at some point.
Right, like if there are primordial black holes and the black holes are merging within the first little while, then you've got gravitational waves coming from this time regime.
Oh yeah, absolutely. Yeah. Then you could use them as standard sirens, I guess, if you could detect them. Yeah, absolutely.
And also figure out where supermassive black holes come from, and maybe explain dark matter and all kinds of good stuff if you can find these primordial black holes.
Exactly, yeah. Like Nobel Prize stuff, right?
Exactly, Nobel Prize all around. So I guess, this is a very mean question to ask you, but I'm going to ask you, what do you think is the most likely explanation for the Hubble tension?
Most likely.
Just what's your gut right now? It's okay.
Okay, sure. I stand by the claim I made in my paper, which is that I think at the end of the story, at the end of the day, the Hubble tension will be explained by a combination of early universe physics and late universe physics, and maybe something on local scales, like a small void or something like that. Now, if you want me to be more specific than that, you are basically asking me which models do I like the most in each sector. I can give you an answer on that.
Well, yeah. I guess I want to know which one seems to have the most evidence, or the easily explained.
So at early times, I don't particularly like early dark energy. I do like a proposed very phenomenological model where the electron mass changes over time. So the electron was, I think, slightly heavier around recombination. This will make recombination occur earlier, and you will lower the sound horizon because of that, simply because sound waves have less time before they freeze. Okay? I like this model quite a bit, with the caveat that on the theory side, it is quite crazy. In the late universe, there is a model I really like, and I think it's promising. It's called Lambda-CDM, where S stands for, I think, sign switch. So it is a model where at late time, so at redshift below 2 roughly, the cosmological constant is positive. It's just plus lambda. And then suddenly it spontaneously switches to minus lambda. Actually, just today, I started looking with a student in Japan at what happens if we combine this crazy varying electron mass in the early universe plus this sign switch cosmological constant in the late universe. So if you ask me maybe 1 month from now, I'll be able to give you an answer of where we land H0 in this model, but I don't know yet. I literally started today. These are two models I find promising, and I think it's worth looking for perturbations around them, in the sense that I think if there is a true model for the universe which solves the Hubble tension, it might be not too far from them.
Mm-hmm. I mean, that idea that it's a combination of factors that come together fits very nicely with our experience in the past. When you think about even just the search for missing matter, not dark matter, but just regular missing matter, like it was bits and pieces, a little bit of this and a little bit of that and a little bit of intergalactic gas. And so if you sort of add up all these pieces, you end up with something that accounts for it. And even same thing with dark matter, like it could just be that, yes, we didn't quite have gravity correct, but also there's particles and also there's black holes and also there's voids that are changing our measurements.
That's likely, I think. In fact, I think we still haven't found all these missing baryons you mentioned. We're still looking for them. I mean, we made lots of progress over the past, especially 5 years. Mm-hmm. But I think we haven't found all of them yet. So
yeah, it is pretty close.
An open probe. It is pretty close, but there's I remember a 10% mismatch at this point, which is still much better than 10 years ago.
Yes, I mean, I kind of remember sort of my last reporting on this, and I think they'd done a measurement of quasar light through intergalactic gas clouds, and were able to account for a large part of the missing mass that sort of closed that gap. But that's a very unsatisfying eureka. It's more this sort of day-to-day grunt work to get to find every last little piece, and yet in the end, the universe is more complicated than we thought, and maybe less interesting.
So I think the point is, there's this quote by I think Neil deGrasse Tyson said once, "Nature is under no obligation to be understandable by us," and I think we can say, the universe is under no obligation to look simple to us. We have a very limited metric of what is simple.
We're, every now and then we got these gifts like E = mc squared, and the rest of the time we get quantum mechanics.
Yes, that's fantastic. Yeah, that's true.
Yeah, it's just not fair. Nobody ordered that, right?
Yeah, exactly. Yeah.
Well, Sunny, what are you obsessed with right now?
Okay, I'm obsessed about dark energy in both on the theory side and on the data side. On the data side, I find very unsatisfactory that over the past 25 years, we've been looking for dark energy in exactly the same way, which is looking for its gravitational signatures. But if you go and talk to dark matter particle physicists, they'll say, oh, we've done that 100 years ago. Now we're looking for its non-gravitational signatures, its particle nature. So I've been obsessing for the past couple of years about new ways to look for dark energy's non-gravitational interactions, which will eventually give us insight into its particle nature.
Dark matter?
Dark energy.
So dark energy's particle nature?
Yeah, exactly. I'm thinking about whether we can figure out the particle responsible for dark energy. If dark energy is due to a new particle, that's pretty much one thing I'm obsessing about. And
not just the vacuum energy nature of space itself, but actually...
Not just that. But now you got to my other theoretical obsession, which is, why is the vacuum energy so small? And I think ultimately... what I'm obsessing about is figuring out if there's some symmetry which protects the smallness of the cosmological constant of the vacuum energy. My hunch is that there is such a symmetry, and it will require the vacuum energy to be exactly zero. And on top of that, small quantum corrections will give the small observed value of the vacuum energy. I'm obsessing on it like literally every day. I walk back from my work to home. It's like 23 minutes. I think about this in my head. Just when I'm, So it's like, 20 minutes a day, 5 days a week. I don't think about it, during my normal working time. I like these things to work in the background and eventually the solution will come up one day, many years from now, probably.
But what you're hoping for is either some kind of mathematics that makes sense or an observation that would confirm that this is possible. And
both. Yeah, exactly. Both of them.
Right. And it must be interesting, like as you look through papers and you think, like for me, when I look through papers, I'm like, are people going to find this an interesting story? Should I cover this? And for you, is like, could a particle be causing this?
Yeah, pretty much.
Yeah, it's interesting. Well, Sunny, it was a pleasure to talk to you. And thank you so much for helping to teach me this part of cosmology, and now I feel better prepared to digest the claims of early dark energy as I see them. Thank you so much.
Well, it was very nice talking to you.
I'm going to talk a little more about my thoughts on this interview that we just did, but first I'd like to thank our patrons. Thanks to David Richards, Mark Anstius, Joel Yancey, Antonio Lofi-Lara, Dustin Cable, Vlad Shiplin, Modso, George, David Giltonhead, Andrew M. Gross, Jeremy Maddern, Josh Schultz, Jordan Young, who support us at the Master of the Universe level, and all of our other supporters on Patreon. I hope you enjoyed this interview with Sunny Vagnozzi. I was definitely struggling to keep up and just make sure that I understood all of the things that he was saying. And this is because we are really in the very early stages. Like, I know you've probably been hearing about the crisis in cosmology for a while now, but it's a big mystery. And we are right in the middle of astronomers trying to solve this mystery. And with a lot of other mysteries that we are now on the other side of, how does the sun make energy? Where do rainbows come from? What are volcanoes? Right? How did we get all these different life forms? We are at the end of hundreds of years of scientists doing very careful work and disagreeing with one another and writing papers and arguing and doing more experiments and trying to get to some level of scientific consensus. And it's very satisfying to go, of course, obviously it was evolution. Obviously, there's fusion at the core of the sun. We know that now, but those answers didn't come easily. Nature is not giving up its secrets. It holds on to them tightly. And so when we're in the middle of a mystery, this feeling that you have where you want resolution, that you're hearing all of these things going on from many different people, many different experiments, people disagreeing, no consensus, this is normal. This is what it has always felt like to people at every time in history. And you're lucky to be living through these mysteries. And the people in the future are going to look back and go, of course, dark matter was this. And of course, dark energy was that. But we don't have those answers yet. We have to find them. And so for me, I enjoy the process. I enjoy the journey. I enjoy hearing people propose their ideas and watch how this science gets worked out in real time, bit by bit, discovery by discovery, as consensus is so slowly reached. And I hope you enjoy this process too. I've got two interviews that I think you'll really enjoy. One goes into more detail about science communication and the crisis in cosmology with Dr. Ethan Siegel. And another goes into, in great detail, one of the measurement methods for figuring out the expansion rate of the universe. And that is a very detailed supernova survey conversation that I had with Dr. Dylan Brout. And we talk about how the expansion rate of the universe has been measured in the middle times with tremendous precision. So two interviews that I think you're really going to enjoy to follow on to this interview. All right. Thanks for watching. We'll see you next time.